So this is a problem that combines a little bit of the kinematics we did in the first few chapters with the Newton's law of forces and friction. A car traveling at 30 meters per second skids to a stop. So he's driving along at 70 miles an hour or something like that, and he locks up his brakes and skids to a stop. The car has a mass of 500 kilograms. This will be an interesting thing to watch. And its coefficient of friction, it'll be kinetic friction because he's sliding, is 0.8. By the way, a car that locks up its wheels uses kinetic friction, but a car that uses ABS brakes uses static friction. We'll talk about that in a minute, or in a slide or two. So the first question is, what's the car's acceleration? And so we can just pick the car when it starts to lock up its brakes and start identifying forces on it. There's a normal force going up. There's a force of gravity going down. And if the car's traveling this way, which way is the friction force? It's this way, right? The force of friction, or we can call it, since we know it's kinetic friction, because I've told you it's kinetic friction, we'll say it's the kinetic friction force. There are a couple of things to note about this. First of all, there's no forward force. The car is driving forward, but there's nothing that your foot's not on the gas anymore, presumably, if you're hitting the brakes. And so there's nothing that's pushing you forward, right? And so if we draw a free body diagram, we have a normal force, we have a friction force, F sub k going backwards, and we have a force of gravity. What direction is the acceleration? Can you answer that question? Hopefully you can. It's this way. We're going to calculate it. Right? Because if the velocity is decreasing, the acceleration is that way. Right? The speed has to be, I have to be subtracting from the speed, and so my change in velocity as it goes from 30 to 0 is negative, which means the acceleration is backward. So this is my free body diagram. I can draw a little coordinate system like this, x and y. And now I can say, look, the sum of the forces in the x direction equals ma sub x. And that says that the friction force, which is in the negative direction, equals ma. I don't have to put the x anymore there because I'm calling it a. And that tells me that mu sub k times the normal force is equal to ma with a minus sign in front, right? That means the acceleration is equal to minus mu sub k times the normal force divided by the mass, right? But what is the normal force? We don't know the normal force yet. Well, to get that, we do the sum of the forces in the y direction equals ma sub y, but that one's 0. Once again, we chose our axes so that the acceleration is along one direction and there's no acceleration along the other. And that says that the normal force minus the force of gravity is equal to 0, or the normal force is equal to the force of gravity, which is equal to mg. You might be inclined to plug in at this point. Please don't. Now I can take this and stick it in there, and I can calculate my a, right? A is equal to minus mu sub k mg divided by the mass. Notice the masses cancel. It didn't matter what the mass was. This could be a truck or a bicycle. What matters is the mu sub k. The acceleration is equal to minus mu sub k is 0.8 times g, which is 10 meters per second squared. And so the acceleration is minus 8 meters per second squared. And so it doesn't matter if it's a truck or a bicycle. You will sometimes hear people saying trucks have different stopping distance than bicycles, than in cars. Usually they don't, not significantly anyway, depending on how their load is distributed. You can have some dangerous things in trucks based on what their load is. But in terms of the physics of how objects stop, all that matters is mu sub k, where the rubber meets the road. And so that answers part A, right? And so now we've got the acceleration. And the next question is, right, how far did the car go? I'm just going to leave that number there. I'll redraw my picture here. I probably shouldn't have erased it. Right? And then I've got it over here somewhere where it stopped. Right, that's the distance it traveled, right? This is V naught equals 30 meters per second, and V final equals 0. Well, if you remember, we had a formula for this, right? V squared is equal to V naught squared plus 2a times x minus x naught. And so x minus x naught is equal to V squared minus V naught squared over 2a. This is how far it travels. These are all the things we know. Once again, V squared is 0. And so I'll just write it down here. X minus x naught is equal to minus V naught squared over 2a. If you remember, a came out to minus mu sub k times g, but we've got a factor of 2 out there. The minus signs cancel, and we get x equals minus v naught squared over 2 mu sub k times g. Sorry, that's x minus x naught. How far it travels. If x naught is 0, you can just call this x, and it's not minus. The minus signs cancel. There we go. Notice that the smaller the coefficient of friction, the farther it goes, right? In our problem, this was 30 meters per second squared over 2 times 0.8 times 10 meters per second squared. I know we already calculated that was 8, right? And so that's 900 divided by 16, which is 56, roughly. What if it happened to be icy, right? And instead of being 0.8, the coefficient of friction was 0.1? Or what if the roads were wet and it was 0.2, right? If this number instead was 0.1, this number would be 8 times bigger. (30 meters per second squared over 2 times 0.1 times 10 meters per second squared. That's 450 meters. This is much larger than this number, right? In dangerous driving conditions, the stopping distances are much larger. You can get coefficients of friction smaller than 0.1 on sufficiently icy and wet roads. And so 56 meters is actually a pretty long way. It's almost 65 yards, or it's over 60 yards. So it's more than half of a football field, right? This is a quarter mile. So if you're on an icy road going 70 miles an hour, your car will skid for a quarter mile before you come to a stop. That's why you see accidents on icy roads. Once again, the mass does not show up in this problem. Okay, here's another friction problem. A block of mass m sits on a ramp with coefficient of static friction mu sub s. And so here's my block, and it sits on a ramp, right? And the ramp has an angle theta, block has a mass m. The coefficient of static friction is mu sub s, so it's sitting on the ramp. And what we do is we keep raising the ramp, increasing the tilt until right before it starts to slide. If we raise it up anymore, it slides. What's the maximum angle you can have under that circumstance? And so we'll start by just drawing some forces here. Right. There's my force of gravity, right, equals mg. Right. I've got a normal force perpendicular to the contact surface. And now I've got a friction force in this problem, right? My force is static friction. And so we're trying to use this to figure out theta. And maybe we don't even know how we're going to get theta out of this, but I know this is a Newton's laws problem, and so I know how to solve it. I'm going to start with a free body diagram. I'm going to pick my, I'm going to draw my forces. Right, there's the force of static friction, there's the normal force, there's the force of gravity. If this, it's not sliding, but if it accelerates, it's going to go this way down the ramp, right? And so I'm going to use a little piece of information to make a coordinate system. And then I'm going to have I've got a little more work to do in my free body diagram, because my coordinate system means that this vector has to be broken up into components, right? And so I'm going to draw my coordinate system on top of my free body diagram. This is my x-axis, this is my y-axis. I've done this kind of thing before. Here is my FGX, and this piece here is my FGY. And if you remember, this angle is theta, and if I do some trigonometry, I can figure out that this angle is also theta. And so I get FGX is equal to force of gravity times sine theta, and FGY is equal to the force of gravity times cosine theta. Now I'm running out of room here, and so I'm going to have to redraw my free body diagram. And so I'll just redraw it right on top of here, I guess. All I really need to do is erase the diagonal piece and put my FGX over here. Right, and now I have four forces: normal force, static friction, x component of gravity, and y component of gravity. And the way you solve these is you just do the sum of the forces, right? And so I can say, look, the sum of the forces in the x direction equals m a sub x. And that's going to be 0, right? Because I don't have, I'm going to, just before it starts to move, it's going to get as high as it can possibly get just before it starts to move. And that means my force of static friction minus FGX is equal to 0, or my force of static friction is equal to mg sine theta, right? Now there's another piece of information we have here, and that's that the friction force is at its maximum value, because if it wasn't at its maximum value, I would be able to raise the ramp still higher. And so this is Fs is equal to Fs max, and that's equal to mu sub s times the normal force, right? Because you remember, if you remember, our definition of the static friction force, just the regular definition of it, was less than or equal to mu sub s times the normal force, right? All right, I'm gonna have to erase the diagram at this point. I'm running out of room here. Try not to be too crowded, right? And so I've basically got all this. Well, I'll leave that up for a few more minutes, right? I'm not gonna erase that part of it, give myself a little more room. And so we're looking for theta, but all we've been given is the mass, mu, and the angle. And so we need to express theta in terms of that. What we have right now is mu sub s times the normal force is equal to mg sine theta. And that doesn't quite get it. We don't know what the normal force is. Otherwise, we were given mu sub s, m, and theta in the problem, so we assume we can solve in terms of those, but I can't have that in there. And so I'm going to look at the sum of the forces in the y direction on this problem and say, let me try that one more time. Sum of the forces in the y direction equals m a sub y. That's equal to 0. And so in the y direction, I have the normal force minus fgy is equal to 0, or the normal force is equal to mg cosine theta. Now, I can take this little guy right here and stick him in there, right? And then this equation becomes mu sub s times mg cosine theta, right? That's what I plugged in for Fn, is equal to mg sine theta. I hope you see that, all I'm doing is I'm solving Newton's laws and then treating them kind of as a math problem, right, to solve for the thing I want. And so notice that mg and mg cancel, and I get mu sub s is equal to sine theta over cosine theta. Hopefully it's still on there, right? That gives me, I'm going to erase this part of it. That gives me mu sub s is equal to tan theta, because sine over cosine is tangent. And so I can say theta is tangent inverse of mu sub s. So that's the maximum angle. If I know what my mu sub s is, I know what I know the maximum angle. By the way, I can also, if I want, so let me take a piece of I can kind of do the reverse of this. So for example, suppose I want to know the coefficient of friction between my iPad and this little metal weight, right? So I can raise up my iPad and measure the angle, right? I'm tilting the iPad upward, up, and suddenly at this angle it starts to slide, right? I raise it up and I get to a certain angle and it starts to slide. That's this angle. And so if I just use a little protractor and measure that angle, then if I take the tangent of it, I can calculate the mu sub s between these two materials, the cover to my iPad and the weight. And so it's kind of the reverse of this. This says what's the maximum angle the ramp can have before the block starts to slide. But I can also say, look, how would you measure mu sub s? And the answer is raise the ramp up until the block starts to slide, and then take the tangent of that angle, and that gives you the coefficient of static friction. And so there are different ways of measuring coefficients of static friction for different materials, and this is one common way. So here's another friction problem. A box mass MB equals 20 kilograms is being pushed by a force F equals 100 newtons directed as shown. So here's my box, right? And it's being pushed at an angle 30 degrees above the horizontal. And the first question they ask us is, what's the normal force on the box? And so we've already got a picture here, but let's annotate it with some forces, right? There's going to be a normal force this way, and there's going to be a force of gravity this way. What else is there going to be? That's equal to the mass of the box times gravity. Everybody tell me? So there's going to be a friction force going back this way, Ff, right? And so, and they're asking us to find the normal force. And you might just look in this problem as we have in previous problems, and say, well, just the normal force is opposite the force of gravity, so it would just be 20 times 10 meters per second squared, or 200 newtons for the normal force. But it's a little more complicated than that because we've got these other forces acting. And so I'm going to draw a free body diagram, clearly for the box. There's not much else to draw it for, right? And I'm going to start drawing some forces here. Here's my normal force. I want the forces originating at the dot. Here's my force of gravity. And so I want this guy going off this way, right? That's my force. And this angle here, if that angle is 30 degrees, this angle is 30 degrees, right? Because it just goes straight on through. And then I've got a force going back this way. That's the friction force. So now I can say, look, this thing's going to accelerate to the right, probably, if it accelerates. And so I'm just going to pick a coordinate system that's going to look like that, right? Y and X. And so the only thing I have left to do is, since this guy is not along an axis, I have to find a Fx and a Fy, so that all of my forces are on coordinate axes. And then I'm just going to, down here below, I'm going to redraw my coordinate system. And so I have my normal force going up. I have Fx going this way. I have Fg going this way. Notice I also have Fy going this way and Ff going this way. And so since this was my angle, if I want to call that theta, and I'm going to say, you know, theta equals 30 degrees, then I know that Fx is equal to F cosine of theta, right? Which is equal to, well, let's just leave it like that for the moment. We'll figure out what it is. We know this is 100 newtons. We know that's 30 degrees, and so that's like 86.6 newtons or something like that. Similarly, Fy is equal to F sine theta. And so now this free body diagram, X, Y, and the acceleration this way, is complete, right? I've got a coordinate system, I've got an acceleration direction. I should have said those in the reverse order. I've got an acceleration that tells me the direction, how to set up my coordinate system. And then I've got all of my forces with components along coordinate axes. The thing that you can see kind of now, why the normal force isn't just equal to and opposite to the force of gravity, is because there's a component of Fy here that's also going to play out opposing the normal force. By pushing downward, you're increasing the normal force, because the normal force has to push up as hard as you push down. And since both gravity and you have some downward component, the normal force is going to have to be larger. And so if I want to look at the normal force, I can just say, well, look, the sum of the forces in the y direction equals ma sub y, and that's equal to 0, because it's not accelerating in the y direction. And so that says that the normal force minus the y component of my push force minus Fg equals 0, or the normal force is equal to Fy plus Fg, but that's just 100 newtons times the cosine of, Fy is the sine of 30 degrees, plus 20 kilograms times, I have to erase some of this here. Tell you what, I'll just write it down here. I'll say it's equal to 100 newtons times the sine of 30 degrees plus 20 kilograms times 10 meters per second squared. Right? Sine of 30 is 0.5, so times 100 is 50, plus 200 is 250 newtons. So whereas if I wasn't pushing on the box at this angle, if there was no force here, the normal force would just be opposing the weight, and it would be 200 newtons. Because I'm angling downward now, I now get a normal force, right? Fn equals 250 newtons. It's increased by my downward push. Right, and so that's the answer to this question, right? And so now question B is, so I'm going to erase this part, and we'll just have to sort of remember it, right? Here's our downward force here. Oops. I'm going to go ahead and use the red again. Fg equals mass of the box times gravity. So for A, we got Fn equals 250 newtons, right? B is, how about if I go back to black? Try again. Lost my black marker. Is, does the box move, right? So for that, we have to imagine this diagram again. We say, look, in order for the box to move, the x direction push force has to be greater than the maximum value of the static friction force pushing in the other direction. If you remember, our diagram looked like this. We had a normal force, and we had the x component of the push force here, and then we had two going this way. One was Fy, and the other one was force of gravity on the box. And then this was my friction force. I was specifically vague about it because I don't know if it's static or kinetic, because we don't know if it moves. But it moves, the box moves, if this number is greater than the maximum value, right? If you remember, the static friction is less than or equal to mu sub s times the normal force, right? And so that means the maximum value of the static friction force is mu sub s times the normal force. And that means that the maximum value is 0.2 times 250 newtons. That was the number that we just got, which is 50 newtons, right? But Fx is equal to F cosine of 30 degrees, which is 100 newtons times 0.866. That's the cosine of 30 degrees. Remember, F is the force that you're pushing with. The x component of that, this piece, is just F times the cosine of 30 degrees. That's this. That's 86.6 newtons. That is greater than the maximum value of friction. And so Fx is greater than Fs max. So yes, it moves, right? This number is greater than that number, so the box moves. Man, I've got my thing switched and it's just got me thoroughly confused. There we go. If I have part C, So I'm going to redraw the free body diagram up here in its final form, right? The one we had down here in the corner. This will just give me a little more space, right? Here's my box. I had a normal force going this way. I had an x component, Fx. And so since it moves, we know that this is an Fk. And then I had two forces going here. I had an Fg, and I had an Fy. Fg for the box. I think I had one shorter than the other. I think I had the shortness reversed, but it doesn't matter. Y, X, and the acceleration is going to be in that direction, right? So that's the idea. Those lines are just not straight enough for me. I'll just go ahead and fix them. I'll call this Fg box, and this Fy. Feels a little better. All right. And so now I've done a whole bunch of stuff with this. Now I just want to say, look, the sum of the forces in the x direction equals ma sub x, right? And that's just equal to the mass of the box times a, right? Well, what are the forces? It's Fx minus Fk equals ma, or they're asking for the acceleration, so a is equal to Fx minus Fk over mass of the box. Oh, I should have a little b there. Well, what is that? We already said that the x direction force was 86.6 newtons, because it was F times the cosine of 30 degrees. It was the x component of the F force. And then the friction force, if you remember, I'll write it over here, Fk is just equal to mu sub k times the normal force. And so it's 0.1 times 250 newtons, all over 20 kilograms. It says A is equal to, so this is a little messy, so let me rewrite it. It's 86.6 newtons minus 0.1 times 250 is 25 newtons over 20 kilograms. And so 86.6 minus 25 is 61.6 newtons over 20 kilograms. .08 meters per second squared. So the push force increased the normal force by adding to the downward force on the box, which the normal force had to accommodate. Notice if I could have changed this problem by having, instead of having this, I could have had a force pulling up, and then that would decrease the normal force, right? A force pushing down increases the normal force, a force pushing up decreases the normal force. And so if you're dragging the thing by a rope or something, where you're pulling on it like a suitcase or something, you're actually reducing the normal force on it. And by the way, that's how people move boxes sometimes. If they're really sticking to the ground, people kind of lift up on them and push them so that to reduce the normal force, so that the friction forces are smaller, because the friction forces depend on the normal force, as you see sort of down here at the bottom.